Today we're going to learn about Gurobi and how to use it to solve mixed integer programs. Before we start, let's take a look at some real-life examples of where Gurobi was used. So first of all, a mixed integer program is a program where you want to either minimize or maximize your linear objective subject to your constraints, and some or all of the variables are integer. So take a look at all of the different applications of mixed integer programs. And in every one of these categories, easily millions of dollars have been saved just by using integer programs. So one big example is the NFL schedule, the National Football League for the United States. There's a $5 billion revenue in the Football League, and Gurobi actually makes the schedule for all the season, for the entire season, all the teams. So some of the constraints here: 256 games in a regular season. Each team plays 16 games over 7 weeks. Each team's opponents are predetermined. Input from 32 clubs. Input from 5 television partners. Entire process takes 2 to 3 months. So here's an example of what a schedule looks like. And to take a look at some of the actual specific constraints, you have things like no team plays more than 2 road games against team coming off their bye. All teams playing road Thursday games are home the previous week. You can see you have all these rules that have to be obeyed, and you try to minimize certain things. Minimize non-division games during hurricane season, and you also have the television stations. CBS, Fox have at least 3 1 p.m. games every week, preferably geographically diverse. All things so that the Football League can ultimately make more money. Now, the solution to this problem used to be done on 24 CPUs. And recently they've had to move to a room full of 16 core servers. So altogether they used 960 cores. That's about the equivalent of 960 computers, CPUs, in order to solve it. What they actually do is they can come up with schedules very fast, thousands of schedules, but they're looking for something really special for the schedule that they choose, and they have to search through all these schedules in order to find it. So there's a good YouTube video on this, and I'll send out a link on how they make the NFL schedule. Okay, another example. It's used in power operations and administering high voltage lines. So basically, without getting into specifics, there's a lot of decisions that have to be made in how power is going to be routed. And every 5 minutes, they solve a problem and figure out how to dispatch the electricity and determine generator clearing prices. So it's very complex, and there's a lot of money in this integer program. And to take a look at some of the history of this, in 2004, PJM implemented a mixed integer program, and an annual savings of $60 million. $100 million annual savings. So there's a lot of money that can be saved by doing big things efficiently. All right. So that's the some of the big applications of integer programming, and specifically Gurobi. Okay, so we're going to start with an example of a Gurobi program. So this is an interesting problem that was written by the student Thomas C., and it was communicated by his professor, Professor Cantor. And I converted it to Gurobi. So basically there's 7 people in the house, and there are 4 chores: kitchen, bathroom, common area, and trash. Trash is the only task that needs 1 person to accomplish, and the other 3 tasks have 2 people assigned to them. Each person needs to rotate through each task twice, but trash only once. Assignments rotate each week. Each person has to have a new partner each week, and no person can have more than 1 task in a week. In the formulation below, we require every possible pair to do at least 1 task together. So this is different from the rules above, but that's what they ultimately ended up doing. Okay, so we're using Gurobi. You can go to the Gurobi website. It's a very expensive program. It's free for academic use if you're a student or a professor, or if you take an online course using Gurobi, and there is 1 or 2. But if you're looking for something free, there's something called Pulp, P-U-L-P. It's a Python library, and it uses a solver called COP-CBC, which is not as fast as Gurobi. It's probably 100 times slower, but still probably fast enough unless you're doing some real industrial work. So it's different syntax, but the ideas are the same. Okay, so let's start. So this is the source code of the program, and you can also type it in line by line into a Python shell, though I wouldn't recommend that. But what I'm going to do is cut and paste certain things. So first, we need the library. That's the Gurobi library. And M is the name of our model. So our model has a name, and we're going to build an integer programming model. Okay, so it's called M. All right, so T is 7. That's easy. That's just a parameter. And here we have 3 sets: volunteers, tasks, and weeks. So let me plug them into Python just to point out you can run this in one shot. You don't have to run it line by line, but I'm doing it line by line in order to teach you and help explain the different lines. All right, so we have volunteers, tasks, and weeks. So if you just type volunteers, you can see it's a set of numbers from 1 to 7. Each number represents a volunteer. Tasks. So this is a set of the 4 tasks. Weeks. We have 7 weeks in our cycle. It just happens to be the number of volunteers also, but so it's just a coincidence. And those are our 3 sets. Okay. A little more complicated is something like this. So pairs is the set of all ordered pairs U comma V for U in volunteers, for V in volunteers, if U is less than V. So let's take a look at this. And what it does is it gives you all possible pairs of volunteers. But the reason we said that U is less than V here is because we didn't want to duplicate. I didn't want to have volunteer 1, 2, and then have volunteer 2, 1. And I also didn't want to have volunteer 1, 1. A person cannot be paired up with himself. So this is a neat trick to make sure that you don't double count anything. Okay. Z is our objective. So let's add Z. And to see what we're actually doing here, Z is our full objective. Gurobi is going to generate this integer program. As you can see, it's quite huge, but the objective line is very simple. It's just Z. Z will be inside the constraints also, otherwise Z would just automatically go to 0. All right. So what we just did is add the variable Z. All right, so here comes some interesting things. So VTW is a big set of ordered triplets, VTW. V is a volunteer, T is a task, W is a week. So let's first take a look at VTW. As you can see, it's a pretty big set. And if you want to look at one element of the set, here's one element. They're separated by ordered triplets and commas. Volunteer V, assigned to trash, week 6. So these are all the possibilities of how a volunteer could be assigned to a task. Another example, volunteer 7 is assigned to kitchen duty in week 5. But they're all here. All the tasks, all the possibilities are here. And a schedule would be a choice of some of these, and a choice for most of them to be 0, and a choice for a few of them to be 1. In other words, we have a variable x VTW. So it's a triple subscripted variable, And this line is meaningless, of course, because it's just a comment. It starts with a number sign. But this is what it means. So this variable will be 1 if volunteer V is assigned to task T in week W, and otherwise it would be 0. All right, so let's add the variable x. We're not just adding one variable, we're adding a variable for every one of these ordered triplets. See, if you take a look at x, it doesn't look like much. If you take a look at one of these, what you have here is the triple subscript, and then a Gurobi variable waiting model update. If we update it, try this again, then what you see is that same first variable looks like it goes to here. So this is the subscript, and this is the variable x sub 6 bathroom 3. Instead of using subscripts, we use dictionary notation. So this is actually a dictionary. This is the key for the dictionary. All right. So something rather complicated is PTW. PTW is the set of all UV, where UV is a pair, T is a task, and W is a week. So let's take a look at that. So if we look at the third to last element here, so 3, 6 is a pair. So this is a volunteer, this is a volunteer. 3 and 6 are volunteers. So 3 and 6 are paired to the bathroom week 6. Volunteer 2 and 3 are both doing kitchen week 7. And then we will have a variable for each pair, whether or not they're matched up. For example, P of UVTW is 1, if volunteer U and V are paired together on task T, week W. All right, so let's add all these variables. Okay, and the variables will look like in the previous case, so I won't display them. All right, now we have our constraints. Each volunteer must be assigned, each volunteer each week must be assigned one task. All right, so let's add this, and we'll explain it in a minute. All right, so it doesn't look like much here, but let's look at what we actually generated with this constraint. So we're going to be adding a lot of constraints in this one line. For each volunteer and for each week, we have a constraint called one task. So there's one line, one row, for every combination of volunteer and weeks. So we know there's 7 volunteers, there's 7 weeks, so there's 49 constraints here. Quick sum means add up all of the x variables, x VTW, but only add up along the tasks. So how does this work? V and W are fixed. They don't change. For each line, V and W stay the same. Those are constants. But inside the quicksum, T is a variable. And T will range over the 4 tasks: garbage, kitchen, commons, and bathroom. So this will be a sum of 4 variables that must equal 1. Each variable is 0 or 1. So what that means is that exactly 1 will be true and the rest will be false. Exactly 1 will be 1 and the rest will be 0. All right, so let's take a look at what the output looks like. So here are the 49 constraints we just made. With that one line. That's why this modeling software is so powerful. One line can generate a lot of constraints very quickly. So for example, for volunteer 1 and week 1, let's take a look here. Does volunteer 1 clean the commons week 1? Or volunteer 1 do the kitchen week 1? Or volunteer do the trash week 1? Or volunteer 1 clean the bathroom week 1? So one of these 4 will be 1 and the rest will be 0, because each one is either 0 or 1. So this is how you tell the integer program to assign each person exactly 1 task each week. Okay. Except for trash, each task each week must be assigned 2 volunteers. So there's 2 constraints here. So let's look at the first one. For each week, for every week, there's going to be 7 constraints here, 7 lines. In each line is going to be a sum. W is the constant, so this is a constant. V is the variable. We're going to sum over all 7 volunteers and say exactly one of them does the trash each week. All right, taking a look at the output. So let's look at trash 1. All right, so here are the 7 trash 1 constraints. Let's go from here to here. And for week 1, exactly one of these volunteers will be doing the trash. In week 2, exactly one of the volunteers will do the trash, and so forth. Okay, then trash 2 says exactly 2 of the volunteers will do each task except for trash. So the way you code that is for every week and for every task if T is not trash. So this is going to cover the 3 other tasks. We want 2 to be selected. So taking an example here, see kitchen, So in week 1, kitchen will be done by exactly 2 people. Person 1, 5, 3, 2, 7, 6, 1, or 4. And as you can see, it doesn't put it in order. The reason is probably because I'm using sets rather than lists, which have an order. Okay. Each volunteer must cycle through each task twice, except trash. So what we're saying is for every volunteer and every task other than trash, if you go over the weeks, if you add up through all 7 weeks, remember V and T are fixed, are constants for each row. Each volunteer will do each task at least 2 times. So let's take a look at 2 times. So let's look at this one here. So bathroom and volunteer 2. These are the constants. These do not change. Volunteer number 2, bathroom. So volunteer number 2, this last argument is the week. At least 2 of these have to be 1, which means it's guaranteed that volunteer 2 will be doing the bathrooms at least 2 times. And notice that trash is left out of this group. That's because of this. Remember, this means not equal to. Okay, now here, we're almost done. Here is a key constraint. This is a bit tricky. We want to minimize the number of times anyone has to do the trash. So for each volunteer, what we're doing is V is fixed. So for each row of our constraint, we have 1 volunteer. And then what we say is count up the number of times that volunteer V has to do the trash. Each time volunteer V does the trash in week W, where W goes through all the weeks, this will be a 1. So if a particular volunteer has to do the trash 3 times, this sum will equal 3. Now, the same Z is greater than or equal to all of the number of times each person does the trash. So if you can say with certainty that Z is equal to 1, then that means everybody does the trash at most 1 time. Okay, so to take a look at that constraint, that's the objective constraint. So here's what it looks like. Notice it does something strange by moving the minus Z over to the left side. It keeps the numbers on the right-hand side. So most programs like it that way. So that's what it looks like. But this Z really belongs right here. All right. If pair UVTW, if pair U and V work together, week W and task T. So remember the variable we had previously. If person U and V work together doing task T during week W, it's 1. So we have some constraints to make sure that everybody gets paired up with everybody else. And let's see, what was the pair of constraints? Let's double check. Each person has to have a new partner each week. So let's take a look at these constraints. So if pair UV, see, we haven't connected the pairs to the x's yet. See, there's no constraints here with the variable p. So far they have no meaning. Now we will give them meaning by relating them to the actual schedule. X is essentially the schedule. Volunteer U does task T, week W. All right, so let's take a look at this constraint. So it's a lot of constraints for every task, for every week, for every pair. So that's a huge number of constraints. That's 7 times 8, 7 times 7. And how many pairs are there? Well, here are pairs, right? Well, there's not too many pairs. I guess we can calculate them, but if you just type the length of pairs, LEN pairs, there's 21 of them. So you can figure that out from 7 choose 2. 7 combinations taken 2 at a time. So what we're looking at here is 7 times 7 times the 21 pairs. So that's a lot of constraints, right? Okay. So if pair UV is assigned task T in week W, then that implies two things. So that implies this must be 1 and this must be 1. In other words, if a pair UV is assigned a task T in a certain week W, then individually both of these volunteers have to be on the schedule for doing task T in week W. So the two constraints really go together, but you do need two different lines for them. You cannot combine them into one line. At least not very easily. Okay. And on the other hand, let's say this is 1, so this is true. Volunteer U is assigned task T, week W, and volunteer V is assigned task T in week W. So this will be a 1, and this will be a 1. 1 plus 1 is 2. Take away 1 is 1. So if both of them are assigned a task, the right-hand side is a 1. Since this is a binary variable, this will be forced to be 1, because it can only be 1 or 0. So this is sort of like the converse. It's the converse of these two statements. If this is a 1, then these two are 1. Now, if both of these are 1 together, then this must be a 1. On the other hand, let's say this is 1, but this one is a 0. Well, in that case, the right-hand side will be 1 plus 0 minus 1, that's 0. Well, anything is greater than 0, so this constraint is meaningless. It's non-binding. It's not restrictive at all. It won't force anything upon P. And of course, if both of these are 0, the right-hand side is a -1, well, it's always greater than -1, so there's no harm done. All right, finally, each pair should do at least one task in 1 week together. So this is a quick sum over all tasks in all weeks. So out of the 49 possible combination of tasks and weeks, you should get one pair together. All right, so to take a look at one task together, as you can see, those pair constraints, there are quite a lot of them. All right, this is a pretty big file. It's we're in the line 2000 already. All right, these are our variables. All right, one task together. So there are 49 possible ways that a pair can be assigned a task in a certain week. So for example, volunteer 2 and 4 could be assigned commons week 6. Volunteer 2 and 4 could be assigned the bathroom in week 5. So there's 49 possibilities, and at least one of them has to be true. So at least one of these numbers should be a 1, and more than one can be 1, but the rest would have to be, the rest could be 0. All right, so let me make sure I add all the constraints here. I'll just copy and paste them. All right, and this command here writes out the LP file. This is the LP file. I believe it was originally IBM's format for solving linear programs, but this is the LP file. So I already wrote it out before. All right, so let's optimize. So let's find the optimal solution. So m.optimize. All right. Now, as I said, Gurobi is very fast. Altogether, there were 1,939 rows. That's constraints, 785 variables, and 495 were non-zero. You can put all these constraints and variables in a giant matrix. That's how big the matrix would be. All right, the pre-solver removed certain constraints and variables that were actually unneeded. And it really saves time, and it shrinks the size of the mixed integer program. All right, so in the end, we're down to a 1449 rows, 638 columns. All right, we have 638 integer variables. All but z was binary. All right, so this is the relaxation is what you consider when you is what you solve when you relax the constraint that all the variables are integer. So if you just allow the variables to be free real variables, then the simplex method will solve in 575 iterations, takes 0.04 seconds, and it gets a solution of 1. So this is a solution to the real linear program, not the integer one. Then it starts solving. Turns out 104 variables are not integer. That's bad because we want them all to be integer. So it uses a branch and cut procedure, and it like we did in class, but something much more advanced. And it slowly eliminates the number of non-integers until it has a solution, and it found an optimal integer solution matching with our relaxed objective 1. So what this means is one person will be doing the trash. So these two lines display that information. I'll cut and paste them here. Most anyone needs to take out the garbage is 1 time. So that's the objective value. m.obj value, that's the objective value. Okay, let's get our solution. So here is the solution. We have to form a dictionary of the solution to the variables. You can't just say what is x equal to. You actually have to get it from the model. So I make a new variable called x sub m to represent the solved value of the variables. So let's get them. So now if you look at them, x sub m, this is the solution. So take a look at a few of these. Person 6 is true. 1 is going to be doing the bathroom week 3. Person 1 will not be doing the trash week 2. Sometimes you get a -0, but that's still 0. Person 3 is false, doing the trash week 6. Okay. If you want to see which ones are true, I put a little for loop to go through the non-zero ones. All right, let me do this part again. All right, so here's the actual schedule. Person 6 does the bathroom week 3. Person 3 does the kitchen week 6. Person 4 does the commons week 6. And finally, to see the pairs, so volunteer 1 and 5 are doing commons week 4. Volunteer 4 and 7 do the commons week 6. And you can see that every possible of these 21 pairs are doing one thing together. All right. So this is looks pretty big, but it's actually still a baby model. A real-life scheduling problem can be quite a bit bigger. If you take a look at, I actually have one running here.
I don't understand.
So I have one running here, and to take a look at how big this is, this model has 149,843 rows, 197,394 columns, and 850,000 non-zeros. And as you can see, it's been solving already for 1,650 seconds, and it actually just found a feasible solution. This solution has a gap of 4%, which means it's 4% off from the best possible answer it could have. But it's going to keep going. And in fact, this model is going to get even bigger and bigger as it progresses through this real-life scheduling problem. And in the end, I believe it'll be twice as big as this, closer to maybe 250,000 to 300,000 rows and columns. So these things can get quite huge, and sometimes they can be solved, but sometimes they're unsolvable. They're just too big to be solved by integer programs. So this concludes the lesson. Notice you can run it directly from Python. It's called jezoot.py. That's the name of this file here, jezoot.py. And you can run it directly and see it does it. You don't have to do it line by line. You get a different solution every time, by the way, or at least you could get a different solution every time. You're not guaranteed to always get the same one. Okay.